Using Ohm's law, phasor relationships, and the Pythagorean theorem, you have derived formulas which enable you to calculate the total voltage, impedance, and current in an RL circuit. Now that series RL circuits have been thoroughly examined, let's see how a parallel RL circuit differs.
According to Kirchhoff's voltage law, you know that the voltage in a parallel circuit is the same across each branch. This holds true for a parallel RL circuit. The resistive, inductive, and source voltages are all equal, both in magnitude and phase.
The same two types of relationships that were introduced in connection with series circuits will serve as guides for parallel circuits as well. They are phase relationships and Ohm's frequency relationships.
Let's investigate the phase relationships on graph paper as was done earlier. As you saw with series RL circuits, the resistive voltage is in phase with the current through the resistor, and the inductive voltage leads the current by 90 degrees. Remember, these phase relationships will always be true for each of these components respectively. The difference with parallel RL circuits lies in the fact that the voltages are in phase. This time, the inductive current lags the resistive current by 90 degrees. Here is the phasor diagram. Notice that it is drawn in the opposite direction, clockwise from the 0-degree x-axis, indicating I sub L lagging I sub R.
Just as phasor diagrams and the Pythagorean theorem can be used to determine total voltage in series RL circuits, they can also be used to find the total current in parallel RL circuits. Let's try an example.
In this parallel RL circuit, I sub R equals 3 milliamps and I sub L equals 4 milliamps. Use this form of the Pythagorean theorem. I sub T equals the square root of the quantity I sub R squared plus I sub L squared. This yields 5 milliamps of total current within this parallel RC circuit.
The other basic type of relationship also holds true within parallel RL circuits as well as in series RL circuits. Ohm's frequency relationships. Once again, there is no relationship between resistance and frequency, and there is a direct relationship between inductive reactance and frequency.
The calculation of total impedance in a parallel RL circuit is done in a similar fashion to that of a series RL circuit.
To determine the impedance of a parallel RL circuit, you can use the Ohm's law relationship just as you did for a series RL circuit. Z equals V sub T divided by I sub T. Let's go back to the example with a 40-volt source and a total current of 5 milliamps. The circuit impedance, then, equals 40 volts divided by 5 milliamps, which becomes 40 divided by 5 times 10 to the minus third. This yields 8 times 10 to the third, or a circuit impedance of 8 kiloohms.
Stop the program and complete activity number 3. When finished, continue watching the program.